Hello guys, and welcome to the session of design of continuous two-way slab. In this session we will learn the design of continuous two-way slab. We will see the steps, then we will see the design, then we will also check the necessary checks, and we will lastly see the detailing of the slab. So the codal provisions that you are required is IS 456-2000 and SP16. So here the figure on the left hand side shows the diagram or plan of the two-way slab. So here the E, which the letter E written in the red is the external strip, and the letter written in the red in the middle M, which is the middle strip, and the green color mesh which has been shown on the corners, all four corners, is the torsion reinforcement, which can be used to avoid the lifting, which will be we will see in the further discussions. So let us move on. So these are the this will be our flow of design. First we will calculate the effective depth, then second we will see the design load, moment and shear, third check for depth, fourth area of steel in tension, fifth check for shear, sixth check for deflection, 7 development length, 8th torsion reinforcement, and 9th figure and detailing. So let us start with the question. So here the question is something like this: design a continuous two-way slab panel 1, 2 and 3 of figure given. So in the figure 3 panels is given: panel number 1, panel number 2 and panel number 3. We have to design panel 1, 2 and 3. So in this video I have taken the design of panel number 1 only, and I have also provided the solution for panel number 2 and panel number 3 at the last part of my video. So subjected to factor load of 8 kN per meter square. So the factored live load is given, which is already has been factored. So here we have written the factored dead load as 8 kN per meter square. Sorry, here it will be factored live load 8 kN per meter square. In addition to the dead load, using M20 grade of concrete and Fe415 grade of steel, load of floor finish is 1 kN per meter square. The span showing the figure are effective span. The corners of slab are prevented from lifting. So in the given data it is provided factored live load is equals to 8 kN per meter square, then the floor finish is given as 1 kN per meter square, and the grade of concrete is M20 and the grade of steel is Fe415. So in this question the width of wall is, or the width of support is not given. So in this I have assumed the thickness of wall as 230 mm. So we will design for the panel 1 only in this session. So the box, you can see this box, these are the torsion steel. Here are also torsion steel. We will see in the further design. So let us start with the step 1. So the first step or initial step is to calculation of effective depth. So to calculate the effective depth, so there is a formula: Lx upon D is equals to KT KC KF L by D basic. So the value of L by D basic, if it depends upon the type of we can say type of slab. So in our case the type of slab is continuous slab. So as per the IS 456-2000 page number 37 clause number 23.2.1, the value for the L by D basic we will get, and as our slab is continuous, so we will take the value of L by D basic as 26. So we have used the value as 26. So the value of Kc and Kf will remain 1 1 only. Now for Kt, as it is a continuous slab, so we have to multiply with 1.3. So we have to multiply with 1.3, and our Lx means shorter span. As for this, there is two dimension, with this is 4 meter and this is 6 meter. So it is provided as 4 meter in the width and 6 meter in length. So 4000 divided by d is equals to 1.3 into 1 into 1 into 26. So we'll have the effective depth small d is equals to 118.34 mm, and we will round off and we will take it as 125 mm. So now after calculating small d or effective d, we will find the overall depth, which means capital D. So capital D is equals to small d plus clear cover plus diameter by 2. So the small d is 125, which we have calculated above. Then we have assumed the clear cover for this slab is 20 mm and the diameter of steel as 10 mm. So clear cover 20 mm and diameter by 2, so 10 by 2, which is 5. So the overall depth we have found as 150 mm. So from this the result is small d is 125 mm and the capital D is 150 mm. So moving on to the second step, design load, moment and shear. So first as we have to find dead load, so dead load is equals to the overall depth of the slab into density. So overall depth we have found as here the 150 mm. So by taking 150 mm, so here overall depth we have found as 150 mm. So converting into the meter, 0.15 into density as 25 for the concrete, so we will get the live load as 3.75 kilonewton. Next, moving on to the floor finish, it is given as 1 kilonewton per meter square. Now we have to total these two values, so we will have the total dead load as 4.75 kilonewton per meter square. Now we have to factor this load, so WU, which means factored load, is equals to 1.5 into dead load, total dead load, plus 8, which is live load. We do not have to multiply the factor of safety with the live load, because in the question the live load is already given in the factored, so we do not have to multiply 1.5. So here 1.5 into 4.75 plus 8, so total factored load which includes dead load plus live load is overall 15.125 kilonewton per meter. So we have to highlight this value, and this will be used for the further calculation. Next, what we have to do, we have to find the ratio of Ly by Lx. So by finding the Ly by Lx ratio, the Ly is longer span and Lx is shorter span. So 6 by 4, we have found the ratio as 1.5. After finding this ratio, you have to move on to the IS 456 page number 91, and over that you will have the table number 26. From that we have to see our ratio. So our ratio is 1.5, so we have to see our ratio is here 1.5. and for panel number 1, there are numbers of, here it is given that type of panel and moment considered, okay, then there are many kinds, 1 2 3 4. For panel 1 we have to see, so for panel 1 case number 4 is suitable. So let us read case number 4. Two adjacent edge discontinuous. So in our case, two adjacent end, this is one adjacent end and this is second adjacent end, so these two ends are discontinuous. So in our case this fits, so we will use the case number 4. Negative moment at continuous edge, positive moment at middle span. Okay, so negative moment at the ends edge and the positive will be at the middle span. Similarly, you can read the another cases, but as for panel number 1, the case number 4 is suitable, so we will use the case number 4, and we will see the row and column. So column number 8 and case number 4, we will have the value. Here we have obtained the value, so this value shows the value of alpha x, and here this value shows the value for alpha y. There will be two values for alpha x, 0.075 and 0.056, from which first will be negative and second will be positive. Similarly, there will be two values for alpha y, first will be negative and second will be positive. So first is 0.047 and 0.035. Now what we have to do, we have to make a table like this, in which at the top we have to write alpha x, alpha y, mx, my, rx, ry, asty and astx. In the initial we have to write negative and positive. So as we have found the value of alpha x and alpha y, we have to write this value in that table as per the positive and negative. Here first it is a positive and second it is a first it is a negative and second is a positive. Initially here it is a negative and here it is a positive. So we have written like this from that IS 456 2000, page number 91. Now after finding the value of alpha x and alpha y, we have to find the value for mx and my. So the formula for mx and my, we will have the formula from the IS 456 2000, page number 91. We will have the formula for mx as mx is equals to alpha x WLX square, and for my is equals to alpha y WLX square, where Lx will be 4, which will be shorter span, then the W will be the ultimate load, which you have been founded in the step number 2. So here, as I told, to highlight the value, this value will be used as the W, so we will use as 15.125 kilonewton per meter. So here we will find the mx and my for first part. So first we will find for the this value by using this value. So alpha x, which is 0.075 into W, which means WU from the second step, 15.125 into Lx square, which means shorter span. So for 4 it will be 4 square. So by calculating it, you will have the value of mx in negative side will be 18.15. So similarly we will find for the this value. So for this value we'll make my in negative portion. So alpha x will be 0.047 into W will be 15.125 into Lx 4 square. So we'll have the value of my in negative will be 11.37. Similarly, we will have the value of mx in positive by using the value of alpha x in positive. So it will be 0.056 into 15.125 into 4 square. So we'll have the value of mx in positive as 13.55. So over here we have make 13.55. So moving on to the mx positive by using the value of alpha y positive. So we will have 0.035 into 15.125 into 4 square. So we'll have the value of my positive as 8.47. From these four values of alpha mx and my, moment in x direction and y direction, in both positive and negative, this the values from these four which we have been calculated, the maximum value should be highlighted, because the maximum value will be used in the further calculation. So from this 4, the maximum value is this, avoid the negative and positive we can say negative and positive markings, because negative and positive just shows the values for the moment. So the maximum value is 18.15, so we have to highlight this value and we will use in the further calculation. So after finding mx and my, we have to calculate the rx and ry, value for rx and ry. So what r means? So r means mu upon bd square. So here how we will calculate mu upon bd square? So first for value 1, which has been shown in red 1, so here it has been shown in red number 1 and here it is red number 1. So we'll do mu upon bd square. So for mu we will use the value as for first as shown in red color, 18.15 into 10 raised to 6 divided by b, which means for 1 meter. So we'll convert into the mm, so 1000 into depth, which will be small depth, which will be 125 whole square. So the value of mu upon bd square for the first part will be 1.16. So we will write 1.16 over here. So for second part or the second number, here we have to find the ry. So for using my we will find ry, which means mu upon bd square for number 2. So mu upon bd square is equals to, what is the value of mu? So value of mu is for second is 11.37 into 10 raised to 6 divided by 1000 into 125 and its whole square. So we'll have the value of mu upon bd square for ry as 0.72. So similarly for the third part, so here for the third part we will use mu as 13.55. So 13.55 into 10 raised to 6 divided by 1000 into 125 and its square. So we'll have the value as 0.86. So we will write as 0.86. And the last one, fourth number, so we'll use for fourth number. So here it is a fourth number. For fourth we will use the value of mu as 8.47. So 8.47 into 10 raised to 6 divided by 1000 into 125 square. So we'll have the value of ry positive as 0.54. So we have to write like this. So we have to fill this table like this. So moving on, next we have to see the check for depth. So our step number 3 is to check for depth. So check for depth, the equation for check for depth is equals to d is equals to under root mu upon rb. So the value of mu will be the maximum value of the moment. So the maximum value of the moment is, here I have been highlighted as 18.15. So value of mu will be 18.15 into 10 raised to 6. Then the value of r. So the value of r will be, here it has been shown that for Fe415 the value of r is equals to 0.138 into fck. So 0.138 over here into fck, it is a 20, and the b is 1000 mm. So we have to multiply with 1000 mm. So we'll have the depth as 81.09 mm, which is less than the depth which we have been calculated from this step number 1, which is 125 mm, which means it is okay. So there is no requirement to change the depth, and it is a under reinforced section. Moving on to the step number 4. The step number 4 is to calculate the area of steel in tension. In the continuation of this table, we have to find the area of steel in Y and area of steel in tension in X both. So for this, before starting calculating the area of steel in tension, we have to find the percentage of steel. So for that we have to find percentage of steel for the all four things. So I have taken the percentage of steel can be calculated from the source SP16 page number 48 table number 2, depending upon the grade of concrete. Here it is, a grade of concrete is 20 Newton per mm square. So the value of percentage of steel can be find by using the value of mu upon bd square, here mu upon bd square, and the grade of steel Fe415. So I have shown for the one value only. Here I have shown for the value of mu upon bd square is 0.54. So the value of mu upon bd square is 0.54, which lies between these two, 0.50 and 0.55, and the our grade of steel is 415. So seeing this column and this row, we have to interpolate this green box, which is 0.143 and 0.158. By interpolating, we will have the value of percentage of steel will be 0.158 here I have taken. So by seeing the value for this 1.16 and interpolating it, we will have the percentage of steel as 0.359. Similarly for Ry negative, as Ry negative is 0.72. So by seeing this value in the table number 2, we will have the value of percentage of steel of as 0.218. Similarly for Rx positive. So like this we will have the values of percentage of steel for four values. Now the second we will do is we will find the area of steel in tension in X negative, X positive, Y negative and Y positive. So here we will see for the first I have shown for the this one only. So to find this value, as we have the formula to find the AST, so the AST is equals to PT BD by 100. For calculating this area of steel in tension, the formula is given as percentage of steel into width into depth upon 100. So for calculating the area of steel in tension in Y negative, so we have to use the value of percentage of steel as 0.359. So percentage of steel as 0.359 into width as 1000 mm into depth as 125 mm divided by 1000. We'll have the value of area of steel in Y direction negative side 448.75 mm square. So we have found as 448.75 mm square. Similarly, if you want to find this value, area of steel in X negative, so we have to use the value of percentage of steel as 0.128 into 1000 into 125 divided by 100. You will have the value of EST X in negative as 272.5 mm square. Similarly, for the value of this as AST Y in positive, you have to use the percentage of steel as 0.264. So using 0.264 into 1000 into 125 divided by 100, we will have the value as 330 mm square. And similarly for EST X in positive. After this, in the continuation of this table, you have to add two more columns showing spacing in Y and spacing in X, which has been shown in the green highlight box. So we have to calculate after calculating AST Y, AST X in positive and negative, we have to add two columns which shows SPY, which means spacing in Y direction and spacing in X direction. So by using I have shown for this one, I have shown for this one, so we will find the spacing. So for spacing, first step we have to do is number is equals to capital AST upon small ast. So the capital AST, which means area provided, which is 448.75 divided by small ast. Small ast means area of bar. So pi by 4 into d square. I have taken the diameter of bar as 10 mm, so 10 square. So we have found the number as 5.71 numbers per meter. So spacing, for spacing it will be equation as 1000 upon number. So 1000 upon 5.71, which means 175.01 mm center to center. So the spacing should be reduced, never, the spacing should never be increased. So I have round off and reduced as 170 mm center to center. So here I have written 10 dia 170 center to center. Similarly for this value we have to do the same procedure, and you will have the 10 dia 280 center to center. Similarly, by using this value you will have the spacing for that will be 10 dia 230 center to center. Here in by using this you will have the value for this as 8 dia 250 center to center. Now I can also use here instead of 8 diameter I can also use 10 diameter, but by 10 diameter the spacing was more than 300 mm. So as per the IS 456 the spacing between two reinforcements should not be more than 300 mm center to center. So for reducing that spacing I have reduced the diameter and provided 8 diameter 250 center to center. Hope you have cleared this how to calculate the spacing and diameter for the by using area of steel in tension. So the fifth step is to calculate or the check for shear. So for check for shear, initially you have to use the equation Vu is equals to Wu Lx by 2. So the value of Wu from step number 2 we have 15.125 into Lx, which means 4 shorter span divided by 2. So the value of Vu we have 30.25 kilonewton. So next we have to do is we have to find tau v. So tau v is equals to Vu upon Bd. So the value of Vu has been calculated above, so we will place the value of Vu as 30.25 into 10 raised to 3 divided by B as 1000 and D as 125 mm. So we will have the value of tau v as the 0.242 Newton per mm square. Now next we have to find the next we will find the tau c1. So for calculating the value of tau c1 we need two values, the grade of concrete and percentage of steel. So first we will find the percentage of steel. So as we have calculated the spacing in y and spacing in x, so by using this value we have to use the maximum value of from this 4. So the maximum value is 10 of 230. So we will use the 10 of 230 and we will find the area provided. So by using 10 of 230 center to center, the area provided we have been founded as 341.43 mm square. So by using this the value should be selected from this center only. Center means from the positive values only. From the positive value the maximum value should be selected. So the maximum value is 10 of 230 center to center. From using this 10 of 230 center to center we have to find the area provided. So area provided we have found as 341.43 mm square. So to calculate the percentage of steel we will use the area of steel in tension as the value of this we have been calculated. So here the AST will be 341.43 into 100 upon 1000 into 125 mm. So we'll have the percentage of steel as 0.273. By using that value of 0.273%, we have to go to page number 73 of IS 456-2000 table number 19, and we have to see the value which comes between these two. So our value is 0.273 and the grade of concrete is M20. So we have to interpolate this value to calculate the value of tau c. So we have found the value of tau c as, by interpolating, we have calculated the value of the tau c1 as 0.37. so we have got 0.37, and so we have to find is tau c. To calculate tau c, we have to do is, the formula for tau c is k into tau c1. So already we have calculated the value of tau c1. Now we have to find the value of k. So value of k depends upon the thickness of the depth, which is shown in the table number, or which is shown in the clause number 40.2.1.1, page number 72 of the IS 456-2000. As our depth of this slab is 125 mm, so it is less than 150 mm, so we will use the value of k as 1.3. so we have multiplied 1.3 into 0.37, so we will have the value of tau c as 0.481. So the value of tau c is greater than tau v, so value of tau c is 0.481 and value of tau v as 0.242. so it is less than, so it is okay, and no shear reinforcement are required. So here the check for shear is completed. Now the step number 6 is deflection check. So there will be for deflection we have to find L by D allow and L by D actual. So first we will find L by D allow. So for L by D allow is equals to 26, as I told in the first step that it is a continuous slab, so we have to use 26. So the value of KT and the value of, so we have to find the value of KT, and the value of Kc and Kf will remain 1. So this value of Kc and Kf will remain 1, and we have to find the value for Kt. So for calculating the value of Kt, we have to first find the percentage of steel. So we have already calculated the value of percentage of steel in this over here in this step of the shear check. So we'll use the value of percentage of steel of as 0.273 only, so we have used the value as 0.273. Now moving on to the page number 38 of IS 456, figure number 4. By going on to the page number 38, you will have the formula of Fs. By using this formula you have to find the value of Fs. So Fs is equals to 0.58 into Fy upon AST required upon AST provide. So 0.58 into 415 into AST required. So our AST required is 330 over here. Our required is 330, and our provide is, so we have provided as 341.43. so the value of Fs we have got as 232.64. so moving on to the graph number 4, as our value of Fs is 232.64 and value of percentage of steel as 0.27. so we have to check the graph by, as our value of Fs lies between 190 and 250, we have to interpolate, and percentage of steel as 0.27. so by using plotting the graph, we will have the value of KT as 1.62. So we'll place the value of kt in the equation of Lx by d allow is equals to 26 into 1.62 into 1 into 1, which we have found the allowable deflection as 42.12 mm. And next we will find the actual deflection. So for calculating the actual deflection, we will do Lx by d into Lx by d actual. So Lx, which means shortest span, 4000 divided by d 125, which is 32 mm. So the actual deflection is less than allowable deflection, which means 32 is less than 42.12, which means it is safer for the deflection. So there will be no failure due to deflection. So it is okay and it is safe. So the next step is step number 7, development length. So for the development length, you can have the formula for the development length from IS 456 2000, page number 42 and clause number 26.2.1. So the clause number 26.2.1 gives the formula for the development length as 0.87 Fy diameter of steel divided by 4 tau BD. So 0.87 Fy. So value of Fy is 415, diameter of the steel is 10 mm divided by 4. So the value of tau BD. So the value of tau BD is question mark. So for finding the value of tau BD, we have to go to the page number 43 of IS 456 2000, clause number 26.2.1.1. Depending upon the grade of concrete, it provides the value of tau BD. So for M20 the value of tau BD is 1.2, so we'll have the value as 1.2 as the value of tau BD. Into we have to multiply 1.6 as our steel is HYSD, so we have to multiply 1.6. So we have found the value of LD, development length, as 470.11 mm. The main formula for the check for development length is highlighted as in the red box, which means development length is less than 1.3 into m1 upon v plus L0. So we have already found the value of LD. So next we will find the value for m1. So for finding the value of m1, we have to use the value maximum value of m. So the maximum value of m, as I told you, so maximum value of m is 18.15. So using the value of 18.15 divided by 2, divide by 2, because when there is a moment over here, it will be distributed over it to one end and it will distribute it to the another end. So we have to divide the moment. So we will divide the moment by 2. So we will have the value of m1 as 9.07 kilonewton meter. So we have done with the value of m1. So next we will find the value for L0. So for L0, the formula is bs by 2 minus clear cover plus 3 times the diameter. So for the bend we will plus, for bend we will add 3 times diameter. So the width of support is 230 divided by 2 minus clear cover is 20 plus 3 times the diameter is 10. So we will have the value of L0 as the 125 mm. So we'll put all the values in this equation, and the value of V, we will use the value of V as from here. We will use the value of V as 30.25 kilonewton, which has been calculated in the step number 5, shear check. So we will put the all values in this equation, which has been highlighted in red box. So the equation is okay, which means LD is less than 1.3 m1 upon v plus L0, which means okay. So no development length is required. So last step number 8, torsion reinforcement. So torsion reinforcement, as I told, that at the corners the cage is provided here. So already the distance has been provided, that this distance for the cage can be calculated by Lx by 5, and the value of Lx is 4000 mm divided by 5, which means 800 mm. So the cage size of cage will be 800 cross 800, which has been shown over here. For more clarity, I will move on to the initial page. Here you can see this is the cage. This is the cage which has been placed at the corners. Now we will move on to that cage for reinforcement detailing. So here you can see Lx by 5 as the size of the cage as 800 cross 800. So here we have found the size of the cage as Lx by 5, so 4000 divided by 5, which means 800 mm. So the size of cage which will be placed at the all four corners to prevent the lifting of the reinforcement, so we'll use the cage. So we have known the size of cage, which is 800 mm cross 800 mm. So next we will find the area of torsion reinforcement. So there is a formula 3 by 8 into AST in Y direction. So 3 by 8 into AST in Y direction we will use as per this table. Here we have been shown that AST 5, so we'll use 330. So here 3 by 8 into 330. So we have found the area of torsion reinforcement as 123.75 mm. Now let us use the 8 mm diameter, as there is no requirement of higher grade of higher diameter of steel. We will use the minimum reinforcement, so we'll use 8 mm diameter center. So we will now find the numbers. So numbers is equals to we will use as 8000 divided by space. We'll have 2. The actual cage will be something like this: 8000 by 8000 and 2 reinforcement. This cage will be placed at all four corners. So step number 9, figure, and its detailing. So the box highlighted in red color is the panel number 1. On to the right side it is the panel number 2, and above it is a panel number 3. So we will see the detailing of panel number 1 in the shown in the red box. So here you can see the slab. So this is the cage which we have been designed in the step number 8 as a torsion reinforcement. Here it is a cage. Also here it will be one cage, and here it will be one cage. So we will just plot, or we will place the reinforcement as per the which we have been calculated. So in the X direction it has been 8 of 250 center to center, and in Y as 10 230 center to center, and for the cage it is 8 400 center to center. So here it shows the section for the slab panel number 1, over which it shows the this is the bent up, alternative bent up, which will come from here and it will end up over here, and this second bent up will come from here like this, and it will over here. Over it you can see here it is a mesh, or you can say the cage is provided above here, and this is the extra top bar here. So this is the reinforcement detailing, and this is the dotted are the reinforcement in Y direction, 10 of 230 center to center. and the width of the support is 230 mm. So this is the solution for panel number 2 and panel number 3. You can verify it, and if you don't, so I can also share the design for the panel number 3 and 4. So thank you for watching the design of continuous two-way slab. Click below over here to see the more videos related to education. Like, share and subscribe. Thank you.